Hello, so today we'll be taking you through our temperature measurement experiment. So we are aware that reliable and accurate temperature measurement is vital in control of many operations in many industries. We need different methods of measuring the temperature according to their different systems. One of the ways is using a thermocouple. Thermocouples are widely used in science and industry. The applications include temperature measurement for gas turbine exhausts, diesel engines and other industrial processes. They are also used in more common places such as homes and offices, in their thermostats and in their flame sensors.
The objective of the investigation was to understand the capabilities of using a thermocouple to take a temperature measurement. The limitations of the thermocouple were then investigated by increasing the length of the wire and then by using Ohm's law and the resistivity equation. A PT100 probe was then used to evaluate the accuracy of the results. The temperature profile of the furnace was then determined by using a thermocouple.
So how does a thermocouple actually work? A thermocouple has 2 points of contact where it's a complete circuit with a return path. The temperature difference between these 2 points leads for an EMF to be produced. The EMF actually refers to the potential for current flow as the result of the charge separation in the conductor. So then these values that we actually achieve, we compare and we check it with a standard table to get the equivalent temperature for that EMF. Good.
The temperature profile of the furnace was determined using the thermocouple. Over a horizontal length of 300mm, the thermocouple was inserted 30mm at a time, giving 5-minute intervals between each reading to allow the temperature to stabilise.
Figure 1 shows the calibration curve. We use the standard tables to find the respective temperatures for each EMF of our data. We did this using interpolation, which is not very accurate compared to the PT100 probe. For DWAR2, the EMF increases as the wire is extended due to an increase in resistivity. Table 1 shows that DWAR1, which contains crushed ice, has the same EMF and therefore the same temperature as the extended wire as shown in Figure 2, Table 2. The EMF of the boiler also does not change much, which may be due to errors in collecting results. We would expect to see a higher EMF using the extended wire as it has a high resistance, and this is because according to the resistivity equation, the length is proportional to the resistance and resistivity is constant as it's a property of the wire.
The values between the thermocouple and PT100 probe are similar and consistent in tables 1 and 2. Table 3 shows the effect of reversing the polarity of the thermocouple. As shown in the data, it doesn't have much of an impact on the EMF and temperature except for the change in sign. The boiler has a temperature of minus 118.74 degrees Celsius, which is not possible, therefore a PT100 probe is the better instrument to use. Errors include using old wires and loose connections, taking an average of the EMF as it kept fluctuating, and using interpolation to find the temperature as the values won't be as precise. In conclusion, to improve our experiment, we should repeat the number of trials so we can remove anomalous results and take mean values.
The PT probe is a more accurate instrument to use compared to the thermocouple.
In industries where thermocouples are appropriately used, such as gas-powered major appliances, thermocouples are a better choice compared to PT100 as it's cheaper and it still has a very good accuracy.
After evaluating the capabilities and the limitations of the thermocouple, it is evident that it is a suitable replacement for a PT100 probe, although care must be taken with the polarity of the system. Thank you for watching our video.